Hi friends, now let's get into what a mean square error is and how it helps us in estimating the signal and comparing two signals whether they are similar or not. In other words, when we trying to find a equivalent signal for our signal, maybe in terms of sum of the basis signals, then we want to know how near the estimated signal has reached to our own original signal, and that is done through finding the error, and that error mainly we define in terms of mean square error. So mean square error quantifies the difference between the true signal and the approximated signal. So we are talking about approximated signal because we are trying to build a mathematical model for our true signal. As it is, we are not able to model it mathematically. Therefore, we try to approximate the real signal through the known signals, add them up, and then the known signals, we know what the mathematical form for them is. So that way we are attempting to reach the original one, and in doing this we want to know how better we could approximate the signal. We want to measure this error. If we could approximate exactly, then the error will be 0, otherwise we will have some error. The mean square error is defined as the difference between the actual signal x of t minus the approximated signal xn of t, where n is the number of basis functions used for approximating this signal. So what exactly this is trying to tell us is, at every value of t, we know what is x of t, we know what is xn of t, we subtract that, and sometime x of t may be bigger than xn of t, so that difference will be positive. Sometime x of t may be less than xn of t, then the difference will be negative. So we don't want them to cancel each other when we add them together. So when we integrate them, we don't want the positive part and negative part to cancel each other. So we want the error to be always available for measurement. Therefore we just square it. So the positive square will remain positive, negative square will also be positive. Therefore when we integrate that, we are integrating this difference square, which is always 0 or positive, no chance of being any negative value for any value of t. Therefore this epsilon will be the total error we have, and the main goal is to identify xn of t such that the epsilon is minimum. So goal is to identify what xn of t should be so that the epsilon, the mean square error, is at its minimum. So here we know that the orthogonal functions minimize the error naturally. So if we make use of the mean square error for finding the similarities, then orthogonal functions will definitely help us in finding minimum mean square error. So as the number of terms in our series reaches infinity, then the mean square error reaches 0. So to make sure that the error is almost 0, then we need to use almost infinite number of terms or infinite series in our approximated signal. So the perfect reconstruction is possible for a complete basis. So when we use all infinite basis functions, only then perfect reconstruction is possible. But practically it is not possible to have all infinite terms of the series, so there will be some imperfection and there will be some amount of error. So this idea is useful in data compression and filtering. The question comes definitely is why mean square error is used in signal analysis. So we have many reasons. The first one is to measure the quality of signal approximation. So when we approximate a complex signal x of t using a limited number of basis functions, these basis functions may be sinusoidals, exponentials, or even polynomials. We cannot represent it exactly. So to represent it exactly, we need infinite components, but we are using a limited number of components. Hence, there will be error between the true signal and its approximation. So we want to find out how much is the error, and this is just an approximation, and it is approximated as a sum of series, and there will be always difference between x of t and x hat of t, and the error e of t is x of t minus x hat of t. So we need a way to quantify this error. So there we need some way to say how much is the error. We can't just keep on talking qualitatively that error is there. We want to make sure that the number, if we put that in the form of number, then we can say that one type of representation gets this amount of error, then other representation gets other amount of error. Then we can compare these two numbers and say that which of the two representations is better. So for that we need a numerical thing or a quantifying. We need to quantify this error, and mean square error gives a single number that tells us how close the approximation is. If it is 0, there is nothing related to one another. So if it is 0, both of them are exactly same, so error is 0, or if it is 1, then there is maximum error. So here what we are doing is we just integrate this over one period and divide that by the total period, so that gives the mean as well the average. The second one is to penalize large errors more strongly. If we know that the error is large, then we should somehow penalize that strongly. So we square it, because squaring it ensures large penalization or error and its square. So the way error changes and the way square of the error changes is different. The error changes, if error changes linearly, then the square of error changes non-linearly, that is almost exponential change you will find. And for small changes, the square may be small, but as the error increases, the square of that increases multifold. And if this error is used to somehow penalize or put that in a loop as a negative feedback to ensure the difference between the actual signal and the approximated signal to be reduced, then the more error, the stronger opposition we get, and the better improvement we can think of in the loop and all that. So all errors are positive, that is the first thing after making square. So positive negative deviations don't cancel out each other, as we were discussing since long. Large deviations are penalized more heavily, since squaring amplifies large differences more. And this is important for engineering optimization. We want the smallest overall deviation in energy sense. So when you're talking about energy, actually we are talking about square of that. So when you talk in terms of energy, the better thing would be the square version. So we get into this energy and signal level concepts more detail in the coming sessions. But yes, now we can only say that if we talk about difference between signals in the energy sense, then we need square. Instead of talking about the values or the difference between the two values of signal and its approximation. The value difference is one thing, that's what we are measuring now, but when it comes to energy, then it will be proportional to square of the values. So here when we talk in terms of difference in energy level, then we definitely would like to have squares. Then the third requirement is it has a clear geometric meaning, because energy, if you look at in the error vector. So using a signal vector analogy, think x of t as a vector, then x dash x hat of t is its projection on a subspace spanned by basis function xn of t. The error e is the leftover component perpendicular to that of the subspace. So we get into more details on all these issues. The mean square error represents the energy of the error vector. So that is the error vector norm square. So the second norm of the energy vector is used, and that will be the mean square error. So minimizing the mean square error ensures that our approximation has minimum energy difference from the original signal. That is the best possible approximation in the least square sense. Then finally it leads to optimal coefficients. By minimizing the mean square error with respect to each coefficient a n, we get the derivative of e with respect to a n want to be 0. Then this leads directly to the orthogonality principle, that the error times the basis function integrated will be always 0. So that is, the error is always orthogonal to the approximation space. That is the foundation of Fourier series and least squares method. So that's some basic idea about mean square error and why we want mean square error to be used in understanding the signals, in understanding the systems, in understanding the quality of the signal, in understanding how signals are approximated and how better they can be approximated. For everything, error plays an important role, and everything we want to talk in terms of energy. Therefore square of the error will be the best one, because square of error will directly relate with the energy, the error in the energy. So the energy of the actual signal minus energy of the approximated signal, that deviation is given by the square of the error. So that's it, all about mean square error. Many more interesting issues to follow in the coming sessions, so please keep watching. Thank you.